everybody. Himanshu this side. Welcome to the lecture number 5 for the chapter Light. So, in the last 4 sessions, I hope you guys have covered the reflection and refraction. So, these are the two most important properties related to the propagation of light ray. So, reflection is mainly the bouncing back of light ray. And when we talk about the refraction, we have seen that whenever light ray changes its medium, suppose it is going from air to water, or it is going from glass to air, or maybe some other oil to some other medium. So that's what we define as the refraction. And when we talk about the refraction, we have also discussed that the light ray usually bend when it is not falling normally. If you do not talk about that case, then usually we have seen that the light ray is bending. And because of that bending of light ray, what we have observed that there are certain phenomena which are happening. So if I recall the example of when a stone is kept inside the swimming pool. So at the bottom of the swimming pool, if a stone is kept, then you would find that that stone is little bit lifted up. So we find that it is little bit lifted up because of the phenomena of refraction only. I hope you have understood that part in the previous lectures already. In the previous section, you have also seen one image that was about the glass slab. There you saw that a light ray was coming and it was getting refracted through a glass slab, and then it was again getting refracted. So two times refraction was happening there. And finally, what do you observe that is quite interesting, right? I will also show you that picture again. If you haven't understood something about that, we will discuss about that in today's class. So now what I'm going to discuss with you in today's class is here. Okay. So in today's session, we will discuss about the calculation of that apparent depth. So you guys have seen in the previous section, in the previous class, that yes, when we look at the bottom of the swimming pool, we find that it is little bit lifted up. Okay. So if it is little bit lifted up, then by how much amount it is lifted up? That calculation we haven't done in the previous lectures. What we have just understood in the previous lecture is that it would be lifted up, and I hope you are now able to draw the ray diagram, and you can show me clearly that how it is lifted up. In today's class, first of all, I'm going to discuss with you that calculation. Now, the numerical calculation, I'll show you how much it will be lifted up. So that part I'm going to discuss with you first of all. And then later on, I'm going to discuss with you the shifting, that if you remember the image which we have shown in you in the previous section, in the previous class, when a light ray was entering a glass slab, it was getting refracted and again refracted. So two times refraction were happening, and it was changing its path. So that shifting was happening. Now how much that shifting is happening, that also we are going to discuss in today's class. So mainly today's class is based upon the numerical calculations. Once we discuss the laws of refraction after that. Okay, so let's begin, right? So let us first of all begin with the apparent depth concept, and then we'll talk about the lateral shift in a slab. All right. So what is apparent depth, right? So apparent depth means, suppose he is the observer standing here, and this is the object. So this is called the real depth, the actual depth from here, from the surface. That's a boundary you can call, or you can say the surface. So this is the real depth. We can write it as some value d. Yeah. And now if you draw the ray diagram, so you can see the one ray is coming from here. All right. So that's a ray. You can see the first ray. Okay. And now after refraction, it will bend. So it is going denser to rarer medium. So that's a denser medium. And outside medium is rarer. He's standing in the surrounding. So air is in the surrounding. So we can assume that air is, so we can say that the air is rarer with respect to the water. Hence, optically, I'm saying optically compared to the water. So what will happen? The light ray would reflect from here. It will bend, right? So now if it is bending, now what this person would say, that this light ray is not coming from this place. For him, for this observer, the light ray is coming this one. So what he would say, that what I'm finding is that the light ray is coming from this place. So actually what he would say, that fish is not that place, at place X. Actually the fish is at a place Y, because the light rays for him, for the observer, is coming from along this line. He doesn't even know whether the fish is there or not at this place, at the position X. What he would sense, what his eyes would sense, his eye would sense that this light ray we are getting, if this light ray we are getting, then he will find that these light rays are coming somewhere from here. And he would say that the fish is at the location Y. And if you see that carefully, then this distance Y from the surface, which is we call the apparent depth. So if I denote it by the symbol dA, so you can clearly say that apparent depth is actually less than the actual depth. So apparent depth is less than the actual depth. So that's what the meaning of apparent depth. Actually, now I would leave it for you guys as an homework. You guys should make another ray diagram for rarer to denser medium. When light ray starts from the rarer medium and it goes to the denser medium. In that case, you will find that the apparent height which we will be getting would be more than the original height. Let me just give you the ray diagram here, and this I am keeping for you guys to feel how it is more. So suppose that's a boundary, and this time the observer is again standing here. All right, and let us take the object to be kept over here. But this time the light rays are going from rarer to denser medium. So you can take this as an object, and now it's your homework. You have to observe that if this height I am taking as h, which is the original height, right, then the apparent height would be, which I'll be getting, would be greater than the actual height. So that's what you have to prove. Okay, the apparent depth part I will prove myself here in the class, right, and the apparent height part you should do as an homework. It would be quite same. I will show you the entire maths here. Okay, so no need to worry, the entire mathematics I'll be showing you here for the apparent depth, and for an apparent height you guys should try yourself. Okay, so now let us begin with the apparent depth. So I'll do some calculations now. Okay, so here we can see we have the boundary here. That's the boundary separating two mediums, and what we have to calculate is, suppose we want to measure like how much lifted this bottom will be seen for the observer who is standing outside. So beyond this, so suppose this has a medium refractive index mu1, and this one I am taking mu2. Okay, and I'm taking the case mu1 greater than mu2. In the end, what I'll do, usually what we find is mu2 is air, so we can put the value of mu2 as 1, but for now I am taking the general numbers. Okay, so basically light ray is going from denser to rarer medium because mu1 is greater than mu2. I hope you remember that from the previous sections. Now, so let us start a light ray from here. From anywhere you can start. Okay, I need some space. I want to draw a big diagram, so I'm starting from this place. All right, so now the light ray would start from here. So first light ray you should always take straight. So when a light ray goes straight, we know it very well that it would not bend. Actually it would refract, but it would not bend, right? So light ray I'll be taking starting from here. Okay, and it is going I think it looks straight to you. Yeah, so that's a straight ray I have taken, and now it would not bend. Actually it would go straight only. The second light ray which I'm going to take is at some angle. All right, and to get the image we actually have to take the two light rays, because after that only I would be able to take their intersection. So this is what, it's a normal line, and now I can call this as the angle of incidence. Okay, so now you should know that how this light ray would bend. It must bend away from the normal. So for the observer who is standing outside, suppose he is the observer. So what this observer would say that I am getting two light rays actually. This is one light ray and this is second light ray. Actually, he would be getting infinite number of light rays, but for our mathematical part, I'm just taking only two light rays. So what he would say that if I want to trace the image, then I need to get the intersection of these two light rays, the light ray 1 and light ray 2. So how he would get the intersection? So he would retrace it back. So when he retraces it back, you will find that the light rays are getting intersected at this place. So basically we are getting the image of the object O at the position I. Okay, so let's do some naming. So let's say this point is A, this point is B, and this we have already told it's O. Yeah. Okay. So for this observer, the image of the point O is being formed at the point I. So if I say this actual height, oh sorry, actual depth is D. O. D original I am referring to. So if original depth is DO, then the apparent depth would be this DA. I hope you got my point. So actual depth is DO and apparent depth is DA, sorry, right? So now actually what we should learn here from here is that apparent depth is coming lesser than the original depth. Original depth was more. So that's why the bottom of the swimming pool, you find that it is lifted up, right? Okay. And that's what happened when you put the pen inside the glass. All right. So here actually, if you have a glass filled with water, then if you put the pencil inside it, you will find that it's like a broken pencil. So why is that happening? Because the part of pencil which is inside the water, that gets lifted up like this. All right. The upper part would remain same because it's still in the air, but the lower part after this place, after this much place, will be getting lifted up, and that's why we feel like it's broken. But actually, it's not broken. It's the same thing only. That's our illusion, right? Not illusion, I would say. That's a phenomena of a light ray. It is getting reflected. Okay. Now we have to find out the value of I. That's the purpose of this class. So let us see how to calculate the value of length AI. Okay. So let us do some nomenclature here. This angle is I and this angle I'm saying R, angle of refraction. So easily you can see if this angle is R, then this bigger angle would also be R. Why? Opposite angles, normal, and that same ray we have retraced back. So that's the angle R. If this angle is R, now we can easily say that this angle would also be R. Alternate angles, right? So they are making a Z. That's how you should always see it. This is R, so this will also be R. Okay. And now let me also extend this light ray. This is a normal line, so I'm extending it till here. And this point we can call C. Okay. Now I will look into two or three triangles, and with the help of that, I'll be able to trying to find out the value of AI. Okay. First of all, we can simply say that AB is nothing but equal to OC, because this is AB and this is OC. So they both are same, the same length. So AB is equal to OC. Okay. Now you look at the triangle, first of all, BCO, because this angle is right angle triangle, right angle. It was a normal ray. So angle BCO in a triangle BCO. What I can say is the tan I. What about tan I? So tan I is equal to perpendicular over base. Perpendicular is how much? OC, and base is BC, right? So OC over BC. And similarly, now you should look at the triangle, this one. A is a right angle here. This angle is 90 degree. Now we can look at the triangle IAB. So when we look at the triangle IAB, what we will find is that tan r is equal to perpendicular, which is again AB, and base, which is again IA. So tan r is equal to AB divided by the base, which is IA. And that's what our interest is actually. We want to find out the value of IA. Okay. So now OC is nothing but it's AB only. So AB over BC. Yeah, you can see that. OC is nothing but it is just AB only. Now here we take a very important assumption, right? And that's what you should always remember also, right? Otherwise we will have to remember a very tough formula, but usually you will find that the numerical questions which we are facing in the JEE exams or NEET or in your Olympiads are also taking the same assumption, and the assumption name is the near normal incidence. So what is this near normal incidence? So near normal incidence is telling you that these light rays are very close to the normal, though this angle looks very big for you to you, but it is not very big, it's a very small angle. I have drawn the magnified image, you can see, you can say, but this angle is not very big, it's a very small angle. So if this angle is very very small, then I can simply write what tan I is equal to I, and tan R becomes R when the angles are small. So we can write it like that. Okay. So this we should always remember, that is, this is for the near normal incidence. It's a very important point. Now another thing, we can apply the Snell's law. Now if you apply the Snell's law at the boundary, so mu1 sine I is equal to mu2 sine R. So mu1 sine I is equal to mu2 sine R. But again, as I said, the angles are very small because of the assumption of near normal incidence, right? So I will just say that mu1 is equal to mu1 I can sine I can write as I only, and sine R I can write as R only. Okay, and let's put the this as equation number 3, this as equation number 1, this as equation number 2. And now my next task is to use these equations. So when I'm going to use these equations, so let us first of all use the value of I from equation 1. So I is nothing but equal to BC, AB upon BC. I'm going to put that value in equation 3. So mu1 I is equal to AB over BC. From equation 2, let's put the value of R in the equation 3, which is nothing but AB over IA. And yeah, AB and AB will get cancelled out. So what you will be getting? Mu1 over BC is equal to mu2 over IA. Now our purpose was to find out the value of IA, because that was the apparent depth. So apparent depth is equal to what? I can write it as mu2 over mu1, and this thing is getting multiplied with BC. So now here we are at the final result. What was IA? IA was the apparent depth. And what was BC? It was the actual depth, the original depth. So this is the apparent depth, which is equal to mu2 over mu1 multiplied BC. Okay. So that's how we get the answer here. So mu2 was less than mu1. Light ray was going from denser medium to rarer medium. Mu1 was greater than mu2. We have already put the condition. So now here also numerically we can say, okay, yeah, let me write BC as actual depth only. That's the actual depth we can simply write here. DO, original depth or actual depth, and DA is apparent depth. So mu2 is less than mu1. So this ratio would be less than 1. And hence it is very much clear now that DA is less than DO. So apparent depth is less than the actual depth. Okay. So that's how we must understand the calculation of apparent depth. So we have got this as a final result. Now let me give you a trick to remember this, right? And the trick is, you must remember the fact that when light ray goes from denser to rarer medium, the things are getting lifted up. So observer is in the rarer medium and the object is in the denser medium. So the things are getting lifted up. So apparent depth is going to be less than the actual depth. So in the numerator, you should put the denser medium, rarer medium. And in the denominator, you should put the denser medium. That's it. In contrast to that, if you want to find out for this case, rarer to denser medium, if light ray is going from rarer to denser medium, then here you will realize after drawing the ray diagram that apparent height is coming more than the actual height, the original height. So what I would say that now the ratio should come greater than 1. So in the denominator, if I say this is the medium 1, which is the denser medium, oh sorry, this is the rarer medium and there's the denser medium. So now in the numerator, I must write the denser medium refractive index, because the ratio must come out to be greater than 1. So that's the easiest way to remember these formulas, because in the end, guys, we have to use the formulas. So we must remember them. So now it's our headache. How do we remember them? Right? The derivations and all are good if we do not get the questions where the near normal incidence is not happening. Okay. So now that's the basic idea about the apparent depth calculations. So now let me use it. Okay. So ultimately, what formula we have got now? That if light ray is going from denser to rarer, then it would be the ratio of rarer medium refractive index upon denser medium refractive index multiplied DO. So that's how I remember the formula. Okay. And if I say that rarer medium is 1, if I say that rarer medium is 1, means mu2 I'm saying 1 for air, which is normally the case. The outside medium, if you get air, and inside medium you get the mu as, let's say, some value, which I'll be giving you just now for the numerical. So in that case, the mu2 will be 1 and the apparent depth will become actual depth upon the refractive index of denser medium. That's how you can remember it if the outside medium is air. All right. So now let us use this thing in a one question. So when we will be using this in one question, then I'll be taking the case when light ray is going from denser to rarer medium. Okay. So suppose you have the swimming pool, all right, or you can say the lake. This is a water medium, so refractive index I'm taking as 4/3. And surrounding is the air, so refractive index is equal to 1. Right. And now there is a fish at the bottom of the swimming pool. Okay. And that fish is at a depth. And that depth is given to us. This depth is, let's say, 40 centimeters. And now right above the fish, very close to it, there is another bird. Okay. So there is a bird here in the air. I hope that looks like a bird, right? So now there is a fish at the bottom, and which is at a 40 centimeter depth, and there is a bird which is at a height of 40 centimeter again. Okay. Now, first of all, the bird is looking at the fish, right? So we have to find out what will be the separation between the bird and the fish. What will be the separation between the bird and the fish if the observer is bird? So when it is seen by the bird, then what is the separation between them? So now I must say that now in this case, the light ray is going from denser to rarer medium, because observer is bird. So that's a observer. So light ray is finally going to the rarer medium, so denser to rarer. Which formula I must use? This formula, apparent depth formula. Okay. So how I would be using it? That from the surface, this bird would find that the fish is at a height, at a depth of only how much? Actual depth divided by denser medium refractive index, and hence in the end you'll get 30 centimeter. Yeah. So that's a 30 centimeter. So means this bird would find that this fish is at a depth of 30 centimeter from here. But that is not the final answer. My question was, what is the separation between the bird and the fish as seen by the bird itself? So observer is bird. So he would say that this is 40 and the fish is already at a 30 centimeter depth, because that's what he would say. So for him, the answer would be 70 centimeter. You can do the reverse also. What would be their distance separation between bird and fish as seen by the fish? So now light ray is coming from the rarer medium. So we must use the apparent height formula. So which will say that in the numerator, you will have to put the denser medium 4 by 3 divided by 1. And then you say that, okay, that is the apparent height. Let's say we're getting 45. Then fish would say 45 plus 30 is 40 is the separation between them. Okay. So that's a simple method to solve the questions related to the apparent depth. I hope you have understood them. Now let's go to the next part. So the next part is about the lateral shift in a slab, the glass slab. Right. This image you have seen in the last lecture, in the previous classes also. What is happening here is that light ray is coming from this way, and then it is getting reflected. All right. So that's the normal here. So it is bending towards the normal. And after this, light ray is bending away from the normal. Yeah. So now we have seen that this light ray is the incident light ray, the original incident light ray. And this is the final emergent light ray. Now, what is so special between them? There's a very good relation we can make between them. First of all, this incident light ray and emergent light ray are parallel to each other. Now, why I'm saying this, you should try to prove it. You can pause the video here. Why is the incident light ray and emergent light ray should be parallel to each other? So you should pause the video here and then you should try to do this yourself. Otherwise, I can give you a solution here. So see, suppose this angle is I and this angle is R1. So this will also be R1 because alternate angles. So what I can say, if this medium is mu, this medium is 1, I can simply write Snell's law as sine I is equal to mu sine R1. And now if you look at the second boundary, the light ray is finally going out at an angle E. So that's the angle of emergence. I'm saying the final angle of emergence. So what is happening there? Light ray is starting from mu at an angle sine R1 and going out at an angle E. So if initial and the final medium is same, this medium is air, the final medium was again air, then these two terms can be equated. So sine I is equal to sine E. So I is equal to E. And which is telling us that this angle is I, this angle is E, they both are equal. Means both the light rays which are going this way are parallel to each other because they are making the same angle with the normal. This is actually not only true with the glass slab. If you take a multiple plane parallel surfaces if you take, right? So if you take a light ray starting from one medium, from here, now it can do multiple refractions. So bending, then bending, bending, then bending. Finally, when it goes out, then if this medium is mu, and if the final medium is also mu, then these two light rays, the emergent one and the incident one, will be parallel to each other. They will be exactly parallel to each other, because you should try this as a homework. Many times JEE and NEET has framed a question over it. Very good level problem in the advanced exam in JEE has come, right? So that's the simple idea to prove it. Use Snell's law for all the boundaries. Okay. Now let me prove this. Like, what if this lateral shift is there, right? So if the lateral shift is present at this place, how I'm able to, like, how I can prove that this thing right now which I'm talking about, right? If this light ray is coming and it is going out, like this. So they both are parallel to each other. So what is the separation between them? The original incident ray and the final emergent ray, they both are parallel to each other. So if they both are parallel to each other, then what is the separation between them? Because in between parallel rays we can find out the separation. So that separation is called the lateral shift. So that's what we call the lateral shift, or you can say the parallel shift. The displacement has happened. So incident ray has deviated in this direction, the final emergent ray. By how much displacement it has deviated, that's what we define as the lateral shift. Okay, so now let us prove this part, like how we can prove this. Okay, so just a second, let me just erase this part over here. Just a second. Yeah. Okay. So now as you can see here guys, that first of all I'm going to take a glass slab, and then I have to prove that it is getting uh, refracted parallel to the incident ray, which we have already done, and then I'll find out the displacement, the distance between these two rays. Okay, so let us take one ray coming at the glass surface this way, and that's the normal, and now it will bend towards the normal because it is going from air to mu, the glass slab, and then it will refract this way, and now it is going from denser to rarer, so it will bend like this. So if I say this angle is I, then I don't think now you have any confusion if I say this angle is also I, because I and E are same. And let's say this angle is R, so this angle would also be R. They both are same angle, right? And now let us do some naming also. If I say this is point A, let's say this is point B. Okay. Now, so our target is basically to find out the displacement between, or the distance between the two rays. This is, if there is no glass slab, it would have gone straight. So I want to find out the separation between these two. Now either you find out this separation or you find out this separation. It's exactly same, because between two parallel lines the distance always remains same, it never changes. So I think I can do that. I can find out this distance also, it would be the same. I am going to represent it by the symbol delta. Okay, so parallel shift or the lateral shift I am going to represent by the symbol delta. Now here, if this is point B, this is point A, then we can mark this as a point C. Okay, all right. Now this was the normal here at this boundary, so let me just extend this normal, and it is coming here. Let's say the point is D. Yeah, so now let's look at the triangle. First of all, we can see the triangle ADB, which is a right angle triangle. Triangle ADB, which is a right angle triangle. Okay, so in this right angle triangle we can say few comments about the angles also. So what we can say, this angle is basically I. All right, and now if you see carefully, then this angle is R, this angle is R, this angle is also R, and this total angle would be I. Why I'm saying this total angle is I? Because this is the normal, and this angle is I because the opposite angle, so that would also be I only. All right, so what I can say about this angle guys, if you see this small angle would be I minus R, because total angle is I, so this small angle would be I minus R. So now I am going to deal with the two triangles. One triangle is this ADB, and second triangle which I am going to deal with is the triangle BCD, because that is also a right angle triangle. All right, okay. Now if you see in the right angle triangle BCD, right, so what I can comment here, what I can say about it in the right angle triangle BCD. Is it BCD? No, it's BCA actually. Sorry. Yeah, it's BCA. B, then C, and then A. So in the right angle triangle BCA, this angle is I minus R. Let me draw this separately here. Right angle triangle is like this. This angle is how much? It is I minus R. All right. And this is 90 degree. This is B. This is C. And this is point A. So what I can say in the triangle BCA, I can write that the sine is sine I minus R is equal to perpendicular, which is BC, and that is nothing but delta only, divide by hypotenuse, which is AB. So from here we are getting delta is equal to AB times sine I minus R. That's the equation number 1. Now I don't know the value of AB. So what should I do to find out the value of AB? So to find out the value of AB, I'll go to the triangle which I have already mentioned there, ADB. So the triangle ADB, it looks like this. So that is the point B here, that is a point A here, and that is a point D here. And this angle is 90 degree, and this angle is R. Yeah. Now what I can say here, what about cos R? So cos R is BD, which is the base, over hypotenuse. Hypotenuse is AB. Let's call this as equation number 2. So now what we can add here? We can say that from the equation number 2, we are getting that AB is equal to BD over cos R. This value I am going to use in the equation number 1. From the equation number 2, I have got the value of AB, which is BD over cos R, and that I'm going to put in the equation number 1. So when I do that, I'll get delta equal to BD divided by cos R multiplied sine I minus R. Now what is BD? That we don't need to worry. BD is this vertical length, which is nothing but what? The thickness of the glass slab, which will be given to you in the problem. We'll be knowing it. So BD I can put as thickness. So delta is equal to T multiplied sine I minus R over cos R. That's the final formula. And that's how you find out the lateral displacement. So this much is the lateral displacement when a light ray goes. So it depends on the thickness, right? So if you increase the thickness, the lateral shift will be more actually. So if you have any glass lab, you guys must try this experiment, right? Okay. And then you can also try it for different angle of incidences. You can change the value of I, and then you observe what is happening, whether the numerically what you're getting is it happening in the nature or not, whether you're able to observe whether the light ray is shifting more or not. So that's experiment you can try at home. Okay. Now let us talk about one numerical on this. So we must remember this formula for Olympiads exam. It can be asked T multiplied sine I minus R over cos R. Okay. So let's do one simple question. A ray of light ray is traveling in a direction perpendicular to the boundary of a parallel glass slab. So that's a glass slab and light ray is coming perpendicular to it. So that's the light ray coming. Will it bend? Not at all. It will go straight. The ray of light is refracted towards the normal? No. Away from the normal? No. Along the same path? Reflected along the same path? No, it will not reflect. There is no TIR here. It does not get refracted. Yes. So that's the right answer. Simple question. Let us do one numerical based question based on the lateral shift of a light ray while it passes through a glass slab of thickness 10 centimeter placed in the air. Angle of incidence is given, angle of refraction is given, but mu is not given. So first of all, you guys can try the question. The formula which we have to use is T sine I minus R divided by cos R. That's it. So we have already derived this formula here, and now I'm going to use it. Okay. So if I show the diagram for once, it would look something like this. The light ray is coming, it is getting bent, and then again it is getting bent. And now all the angles and everything is given to us. This is 60 degree and this angle is 45 degree. Let us apply the Snell's law at the boundary, this boundary Mn. So sine 60 is equal to, outside the medium is here, so I'm just writing 1. Refractive index of glass slab multiplied sine 45 degree. And now you know the values, root 3 over 2 is equal to mu whole by root 2. So mu will be equal to how much? We'll be getting from here that mu is equal to root 3 over 2. Root 2 will get cross multiplied and it will become root 3 by 2. We have got the value of mu. Why did I find the value of mu? Was it required to me? Not, right? So simply just I calculated the value of mu also, right? Maybe if it is required. So because you can see here in the formula when we derived it, right, I have just used that sine I minus r is equal to delta over AB, right? And then again I use that this thing that in the triangle, another triangle, so there was no need of using Snell's law. That's why we do not see it. Okay, the presence of mu in the formula. Now we will say that this is mu equal to root 3 over 2. So now let us use the formula delta is equal to t multiplied, so thickness is 10 centimeter, okay, and then sine I is 60 minus 45 degree angle of reflection divided by cos angle of reflection 45 degree. Okay. So delta is equal to what? So delta will be equal to tan sine 15 degree. Cos 45 is 1 by root 2. So that will become 1 by root 2. So I'm just writing it in the denominator 1 by root 2. And finally you will get tan root 2 sine 15 degree. So you can keep the answer like this. Now that's a lateral shift we have got. They could have asked you something else also in the same question. What is the displacement traveled by the light ray inside the glass slab? So in that case, what I would have done, I would have calculated the value of mu. Yes, of course, because in that case they won't give you the angle of reflection then. So we'll calculate the value of mu and then we'll find out the angles. And after finding the angles, we will get the distance traveled because thickness is given to us. Because this is the distance traveled by the light ray inside the glass slab. So these kind of questions are being framed on the lateral shift of a light ray. So that's all guys. Now we have discussed about in today's class, the rectangular glass slab. So, and apparent depth concept, that things are getting lifted up by how much separation they're getting lifted up. That thing we have also derived in today's class. So that's all. So I hope you have understood the lecture. And if you have any confusion, just put it over the PDF. All right then. Thank you so much. Bye bye.